Hello. We'll go ahead and pick up where we left off last time. We talked about some basic concepts and definition, and then defined voltage. We talked about it as electromotive force or potential difference or voltage, and we gave it the symbol V. Sometimes you'd maybe see the symbol E, but we were going to use the symbol V, and found that it was the work done in moving the unit charge. And really, with the garden hose analogy, then related it to pressure. Then we talked about electric current and found it was the time rate of change of charge, or if you will, the number of electrons passing a point in a conductor. And we gave it the symbol I and the unit of an amp. And this was flow. So we tried to be very careful that voltage is pressure across something, that current is flow through something. And these we came up with these notes from last time's lecture if you want to go back and look at the development there. We then put those two together in terms of Watt's law, named after, of course, James Watt. And we saw that power was equal to the product of current times voltage. And with looking at a unit analysis, we got power in terms of watts. And that's where we had left off. We're going to go back and I'm going to talk about Ohm's law, revisit Watt's law. But before we head on, I wanted to talk a little bit about safety, talk about the concept. Oftentimes you'll hear people talk about current kills. Okay, and if we were to do some research and whatnot, usually you could have someone get killed about 1/10 of an amp. Okay, let's say amp will kill someone 1/10 of an amp, and we might, if we were to go and look at the battery or in your car, it's quite capable of producing 500 to 1,000 amps. So quite a bit more than 1/10 of an amp. Even a small battery could produce way more than a 1/10 of an amp. So why aren't we having people getting killed when they're replacing a 12-volt battery in their car, or replacing batteries in a flashlight? Why don't we just have warning stickers all over like we have on other devices that we see around? And that's because current kills, but you have to have enough voltage to push it through the skin. Typically, skin has fairly high resistance, so maybe we should modify this expression. Current kills with enough voltage, or maybe we should recognize that as pressure. Okay, so if we have enough voltage or we have enough pressure to put that through the skin, then you can get into to big trouble. Now, the question oftentimes comes up at this point is how much voltage is enough? Well, it really depends. Is your skin wet? Is it dry? Is it in good repair? Does it have a cut? Something like that. It can vary. I've actually had a cut on my hand and been able to feel 12 volts. Some people will test a battery on their tongue. I'm not sure how smart or fun that is, but so different parts of the body, whether it's wet or dry, all changes. I do know when I start thinking about things getting quite a bit more dangerous, if we look at 48 volts, 36 volts, 48 volts, or on up from there, that's quite a bit more dangerous than 12 volts. So something to think about. You're never going to find someone saying a hard and fast number that this is the number that will kill you. Anything below it won't kill you, because it differs from person to person. But you start getting into 36 volts, 48 volts, you have to be much more careful than you do down at just a few volts. And this also, our garden hose analogy holds well on this also. We could say that water kills with enough pressure. You go and you play in the garden hose at maybe a 50 to 100 psi, no problem at all. You start thinking about playing with a pressure washer at 2,000 or 3,000 or 4,000 psi. That will have a significantly different outcome, as that is enough pressure to push it through your skin, and you could have real problems. So that our garden hose analogy holds well there also. Well, and going back and looking at our garden hose analogy in terms of Watt's law, that we might visit that one more time. We could use a light. Let's say that we had a light bulb that we were running at 120 volts, and we might then be able to run at just maybe a fraction of an amp. We could read by that, right? Okay. Or if we were to run it at 12 volts, we'd need how much more current? We'd need 10 times the current, wouldn't we? If we look at a situation, we'll relate this back to this. If we're running at 120 volts and 1 amp, that's what, 120 watts, isn't it? And we could compare that. I mean, that certainly, we could go get a light bulb, plug it into 120 volts at 1 amp. We get a lot of light out of that and do some good things with that. Or if we were to run it at 12 volts, we would need what? 10 amps to get that 120 watts. We could read with both of those, do good work with both of those, but one would be a relatively high voltage, a relatively high pressure system, and a low flow. This would be a relatively low voltage, a relatively low pressure, and a high flow. Disadvantages and advantages. This is higher voltage, probably going to be more dangerous. The advantage there is you can get by with a much smaller wire because the current is a tenth of this. This one you're going to have a much larger wire. If you've ever compared the size of the wire, not necessarily the insulator, but the wire in an automobile versus in a house or something like that, you'll notice that for what it's doing, usually the wires are a lot larger in the automobile. Maybe we should say a word about AC and DC at this point. That's really just looking at a reference with respect to time. So if we look at voltage or current, over time, if we have DC, it's kind of boring. It's like that. There's DC. And if we have AC, maybe it's doing something like that. It's changing with respect to time. For instance, if you're in a building or something like that, the lights are probably powered with AC, and they're literally turning on and off 60 times a second. Whereas if they were powered with DC, they would be on all the time. Well, most of our work this term, we'll get into AC towards the end of the term, but most of our work this term is going to be DC. That seems to be a little bit easier, and we'll build a nice foundation with that as we go into AC. Once we understand DC, it's pretty easy to transition then into AC. Certainly, there was a big battle in divvying up, deciding whether we were going to electrify the nation with AC or DC, and folks like Westinghouse pushing for AC, and Edison pushing for DC, and all the ghoulish experiments, electrocuting dogs and elephants and things like that, trying to convince the general public how much more dangerous the other person's current was, trying to get favor for their current. So we'll talk a little more about that and the implications of that when we talk about resistance in a little bit with Ohm's law and so forth. The other thing, I don't want to get too sidetracked with AC and DC, is going back and looking at this voltage and current. We talk about the magnitude here, and most people are pretty comfortable with the magnitude, but it also has direction. So it has both a magnitude and a direction or polarity. Okay, so current is probably the easiest to talk about if we were to have some sort of a wire like this, and we said that we have 4 amps traveling down it like that. That would really be the same situation as if I were to say that I had minus 4 amps going in that direction, because if I were to get rid of this negative sign, I couldn't just arbitrarily remove that, but if I remove the negative sign and flip the arrow, then I would get back to that situation. So this is, of course, the same. So if we have 4 amps traveling this way, that'd be the same as minus 4 amps traveling that way. And it's probably important at this point to talk about what current is. We're going to say it's the movement of positive charge. Flow of flow of positive charge. Now, we know that probably physically it's electrons flowing around. Where did this come from? Well, Benjamin Franklin first postulated that current was the flow of positive charge, and we've just stuck with that. We've been vindicated as engineers in the last 50 to 70 years with a solid state design, because now you have electrons going one way and you have holes going or holes of the absence of electrons going the other way. So sometimes people will talk about, well, do you use the flow of electrons, or do you use the flow of the holes? The holes being thought of as a positive thing. If you've come from the military, or you've come from a technology program, 2-year tech program, you probably studied the flow of negative charge, the flow of electrons. Engineering, by and large, we study the flow of positive charge. If you were to pull the books on this, and the 2 big books are by Nielsen and then let's see, what's the other name? You've got Nielsen and Irwin. Those are the 2 big books in this. We're using Nielsen's book. But if we were to go another book by Dorff and whatnot, if we were to go and get some books on this, by and large, most of them, all of them that I've seen recently, for engineering students, use positive charge flow. So if you go to the library and you grab what you think is a good book, be careful of that. Look at the front of the book. Hopefully you're reading in your book in chapters 1 and 2. And it's talking about the flow of positive charge. I know that the Nielsen book is indeed. So if you pick up another book, make sure it's doing that, because it'd be a little confusing in terms of the signs and whatnot. Now, in the end, if we start a problem with positive charge flow and end it with positive charge flow, we will get the same answer as someone that starts it with negative charge flow and ends it with negative charge flow, but you don't want to switch midway through. So it's important here, if you go and select a book or something, make sure that it follows that convention. If you've had some previous education, I mean, you can continue to think of a negative charge flow if you want. It's probably going to be easier for you to maybe do a kind of a rewrite and start with positive charge flow if you're going into this business. So the flow of positive charge. That brings up a point. Then if we have something going through let's say that this is a source. So I have current. I have some current going into a source, and I will differentiate this here. Let's say that we have a load. Being very consistent there. We've got a load, and I've got current going into this load. Okay. So let's say that this is 4 amps. Likewise, this is 4 amps, so it's not a negative number or anything. You're not messing around with that. But if you take 4 amps, which is a whole bunch of positive stuff, right? We said it was positive charge flow. We've got all these positive things. You've got 4 amps positive here. If this is a load, the load is going to go from positive to negative, isn't it? So this would be positive here to negative there, because if you have these positive things, opposites attract, right? So you got all these positive things. It wants to get over to here, so it's going to give up energy to do that. We're going to have then power coming out of that. Now, what if we have all these positive things here going from a source? It's going to go from negative to positive because we're going to be putting power into this, right? Because you got all these positive things, they want to hang around here with the negative. But we're going to put power in to elevate them up to this positive and move them on. So as you go through something that is a source, you're going to go from negative to positive. As you go through something that is a load that you're getting energy out of, you're getting power out of, you're going to go from positive to negative. Okay. So we might, maybe I'll put this in here, and we could say when current enters the negative terminal, so when current enters the negative terminal, power is supplied. So here we have to be supplying power. When current enters the negative terminal, power is supplied. It is a source. And of course vice versa. So that's something to think about. Well, what about voltage? Does voltage have a polarity? It sure does. Let's deal with that. So let's say that I have a circuit here and a couple of terminals sticking out, and I can talk about this as A and B, and maybe I will say that voltage AB is equal to minus 10 volts. Okay. And the way this is actually read is that's the voltage at A with respect to B. Okay, voltage AB. So I've got this negative sign there. I'd probably like to get rid of that negative sign. I can't just cross it out, but I could cross it out if I were to change this polarity here. So if I come over here, much like I did to the current, and we've got A and B, and if I get rid of that negative sign, I could say that the voltage AB is equal to 10 volts. And what am I going to have to do? I got rid of that negative sign there, so I need to switch this and have something like that. Okay. So these are the same. Okay. Those are the same. And which terminal is higher polarity? Not higher polarity, has greater potential. B has the higher potential. Okay. B has higher potential. Well, a lot of times students, this gets a little confusing with voltage. They're pretty comfortable with coming up with a magnitude, and okay, I'll kind of fake the sign. Well, that gets problematic. Let's go look at a battery. I mean, we got the battery here, and we have the terminals, the die-hard battery. If you're going to jumpstart something, the polarity becomes very important, doesn't it? Okay, you might, if you're helping someone jumpstart their car, you might say, "Hey, are we putting the red on positive today?" You're most worried about the polarity. You're probably not asking, "Well, you know, is your battery 12 volts or is your battery 13.5 volts?" That's probably not as big a deal as the polarity. And if we were to talk about the polarity here, we could sometimes do this with an arrow. We could say that this is 12 volts. That's positive 12 volts, isn't it? This has the higher polarity. So if I were to come over here and draw this arrow this way, what would we have? We'd have minus 12 volts, wouldn't we? Okay. You could think about this a little bit like a potential energy argument for the mechanical folks or the civil folks in here. If we were to look at the potential of a person up here and a person here, this person has positive potential with respect to this person here, whereas this person has negative potential with respect to that person there. Okay. Well, going back to this arrow nomenclature or this subscripting, let's talk just a little bit more about that. Let's say that we have a circuit here. And we'll say that this is plus and minus 10 volts. I could say this is A and B. What would voltage A, B be? That's the voltage at A with respect to B. That would be positive 10 volts, wouldn't it? What about the voltage at B with respect to A? Well, if I wanted to draw voltage A with respect to B, this is voltage A with respect to B. The head of that arrow would go at A, wouldn't it? That would be 10 volts. What if I wanted to draw B with respect to A? So I'm going to have something like this, aren't I? I'm going to have the voltage here down here at B with respect to A. There's the voltage at B with respect to A, and what would that be? That would be that minus 10 volts. Again, the same as if you were to look at this potential energy argument going from there to there or back down to there. So be careful of that. That's probably more important than magnitude, but a lot of times it's a little confusing and students tend to try and avoid that. So really dig in. Again, I implore, read chapter 1 out of your textbook, read chapter 2 out of your textbook, practice on some of the homework problems, and really dig in and get this. I think it will pay off well for you. Now going back and talking about power, we had that page 5. So power is equal to current times voltage, and we just found out current could be positive or negative, and voltage could be positive or negative. So the possibility for power to be positive or negative. So what we use here is we use the passive sign convention. The passive sign convention is just to keep the signs on V and I. Keep the signs on V and I and multiply. So if I is positive and V is positive, power is positive. If I is negative and V is negative, power is still positive. But if either one but not both is negative, then you're going to get negative power. Well, what does this mean? If you have positive power, we have power is absorbed. Whereas if we have negative power, it is supplied. Okay, so when we go down and we buy a heater and it's a 1500 watt heater, that's a positive number. It's going to be absorbing power. We have to pay the power bill for that. Whereas if we go to buy a generator, if it's a 1500 watt generator, that would be a very big generator, but if it's a 1500 watt generator, it really should say negative 1500 watt generator. Now, no one likes to sell a product with a big negative on the front of it, but following along with this, if it is supplying, it would be a negative value. If it is absorbing, it would be a positive value. So when you add these together, what you supply has to equal what's absorbed. Conservation there. One last thing in terms of conventions and things like that is typically, most of the time, and of course whenever we say most of the time, we will usually then break this on a fairly regular basis, we use uppercase for constant. So when we're dealing with DC or constant values, we're going to use current as I, voltage as V, power as P, and so forth. And we use then lowercase for variable. Oftentimes a function of time. When we get into AC, we'll talk about it as a function of time. When we get into natural response later in the term, we'll talk about it as a function of time. If something is variable, we'll use I, or maybe we'll even say I of t, and we'll then use V or maybe P. Okay, so not everyone follows this. I'll probably break this plenty, but normally if it's a constant value, if it's a DC value, we use uppercase. If it's a time varying, something that's changing, we will use lowercase. Okay. So let's see if we can put this together in some kind of an example. Switch pins here. I think that one's a little tired. So let's say that I have a circuit. We haven't talked about elements yet, so maybe I'll just set this aside. Let me redo that. Okay, let me try this again. Apologize here. Okay, so we're just going to use these little clouds, and I'll say that this is cloud A, and I don't know what that is. I don't know whether it's a source or a load. We're going to talk about those real quick here, but I think this will be a good example before we do that. And maybe we'll say that in the this circuit has 3 amps traveling around clockwise around that, and we could say that across here we have plus and minus 20 volts across that. Again, we've got voltage across, we have current going through, we have this B value over here that's positive here and negative there, and that's minus 15. And then we've got the C element, whether it's a source or a load. It's positive and negative 5 volts. Okay, well, first off, I probably want to change this out, right? So I'm going to say I don't like this negative sign. That's hard for me to deal with, so I can't just get rid of it, but if I switch the polarity I can get rid of it. So I'm going to say that that is positive 15, and then I'm going to say that that's positive, and this is negative. So I'm now going from positive to negative. Okay. Now if I look at this current here, I have 3 amps going like that, right? So 3 amps is coming into the negative terminal. So I could say then that the power here for A is going to be 3 amps times 20 volts, which gives me what? 60 watts. Okay, and is that current entering the negative terminal? It's entering the negative terminal. What do we say about that? Let's see here. When current enters the negative terminal, power is supplied. It's a source. So it is 60 watts supplied. Okay. Well, let's come up here. This 3 amps continues on. Okay. We have 3 amps here. We have 3 amps here. There's no turnoff for current. We don't have a current heading this way. It's going around the perimeter of this, so we still have 3 amps there, right? And now it's entering the positive terminal. Okay, so I could say that power for B is equal to 3 amps times 15 volts. I'm going to use, because I've got the positive here, I'm going to use positive 15 volts, which gives me what, 45 watts. And if it entered the positive terminal, that must mean it's absorbed, right? Okay. Well, 60 watts supplied, going back to our convention here, I have, let's see, right there. If it's absorbed, it's positive. If it's supplied, it's negative. So this should really be what? Minus 60 watts. 45 watts absorbed should be plus 45 watts. Well, let's finish up with C. Power in C is going to be what? Again, you got 3 amps. You'd have 3 amps times what? 5 volts, which gives me 15 watts. It enters the positive terminal, so it's absorbed. And we can say then positive 15 watts. So when I add this up, what do I get? Minus 60 plus 45 plus 15 is 0 watts. And when I add this up, or I look at this, I see that my supplied has to equal the absorbed. Okay, that will always be true. What you supply has to equal what you absorb. If you could find a device where that you could absorb 100 watts and only have to supply 50 watts, I'd suggest you drop the class and start to sell the product worldwide, because you'd be fabulously wealthy. The world doesn't work like that. Whatever we absorb, we have to supply, and quite frankly, sometimes it's not even that good, because we have losses in there. We're probably going to have to supply more than we get useful work out of, but we could consider the losses in this accounting here. If you choose not to deal with this supplied and absorbed and use the sign here, negative for supplying and positive for absorbing, again, that totals out to 0. So hopefully that's a good example. Well, hopefully we'd like to have a circuit that's a little more interesting than having these clouds and whatnot on it. So let's start to talk about some circuit elements. So the circuit elements that I want to start out with, start out with something like this, where I'm going to have some voltage here, maybe something like this, where I'd have some current here. Okay. And I'll draw something like this. We'd have some voltage here. So this is an independent voltage source. This one is an independent current source. And this one is a battery. And for our purposes, we're going to model this battery just like this independent voltage source. And that's not always a great model. But for our purposes, if you see in your homework problems or in lecture, if someone has drawn it like this, you could think of it just as well as that. So let's talk then about the independent voltage source or the independent current source. Anytime I see the term independent, I'm kind of curious, well, what in the world is it independent of? Well, the independent voltage source is independent of current. No matter how much current we have going through this, how much current you have going through there. So if I draw another one of these down there, something like this, it's in a circuit somewhere. No matter how much current we have going through there, it's going to remain a fixed value of voltage. Now, is that a good model? Yeah, over some ranges. If you look at your automobile, whether you turn the fan on or the seat heater or the air conditioning fan or compressor, the voltage is probably going to remain fairly constant. If you start to have big demands on the voltage in terms of several hundred amps, maybe starting a stubborn engine or something like that, then when the current gets really high, the voltage may drop down some. Okay, but over reasonable ranges, this is probably a pretty good model. Well, what about the independent current source? The independent current source is independent of the voltage across it. Okay, is that always true? Yeah, for reasonable values. So if we have something like this, we've got some current here, and we look at the voltage across this. No matter what that voltage is, it's going to maintain that same current. Ideally, that would be over all values of voltage. In a practical sense, they would have to be over reasonable values of voltage. If you have no potential drop across there, you're going to start to have some problems. So these are independent. Okay, so we talk about independent voltage source, we talk about independent current source. Then we've got some different ones, and if you were with us for GE101, we probably talked about those. We didn't talk about these, though. You could have a dependent sources. So I could start out with this. There's 4 possibilities here. They are diamond in shape, so we don't confuse them with independent. And we have 2 possible combinations for a current source and 2 possible combinations for a voltage source. So what we'll have here is we might have some variable. Maybe we'll say that this is alpha, times some voltage somewhere else. Okay, this would then be a voltage-controlled voltage source. So this value here for this voltage source would take on some factor alpha times the voltage somewhere else. Somewhere else in the circuit there's a voltage, we multiply it by alpha, and that's the voltage we get here. So this is voltage-controlled voltage source. Or we might have some other factor, beta, and it could be a really big number, a really small number, times some current. Here, this one's going to be unitless. Here, this one's actually going to have units to convert currents to volts. So if we have some current somewhere else, we multiply that by beta, and that gives us a voltage value here. So this voltage source is now controlled by a current somewhere else. This is a current-controlled voltage source. Okay, and the same thing happens with a current source. We could take alpha, beta, I guess we'll get to gamma. Gamma times I. So here we have some factor times some current somewhere else. Somewhere else there's a current. We multiply that by a factor. This is a current-controlled current source. Whereas here we might delta times V. So we take some voltage somewhere else and multiply it by this delta, this factor. Maybe it's 10, maybe it's 100. Excuse me, I don't know what it is. Whatever the circuit dictates. Here, this is going to be unitless. Here, this is going to have units to convert voltage to current because we have voltage controlling a current source. So this is a voltage-controlled current source. Okay, voltage-controlled current source. So I have a voltage-controlled voltage source, a current-controlled voltage source, a current-controlled current source, and a voltage-controlled current source. A real good model of one of these is a transistor where we can use a very small current in one location to control a much larger current somewhere else. So maybe you've seen these devices that you touch or something like that. It uses a small amount of current through your body or static electricity, depending on what it is, to control a much larger current somewhere else. A transistor is a great example of one of these, probably this one in many regards, a current-controlled current source. So those are all of our elements. We're going to group the battery and the independent voltage source together. We're going to have the independent current source, and then we've got these four possible dependent sources. Okay, and the way we analyze circuits, if we have these dependent sources, these diamonds, that will be a little bit different. These will be more trying. That's why we didn't see them in the Introduction to Engineering class. So those are our sources. Okay, we have independent here, we have dependent there. Let's talk then a little bit. I don't know that we'll get finished up on this, but let's talk about loads. There's three possibilities for loads. We could have resistive loads. The symbol for a resistor is going to look like that. We could have a capacitive load. The symbol for a capacitor looks like that, or sometimes we'll draw them like that. It means a little bit different whether it's electrolytic or not. And then the inductor. Probably put or here. There we go. The inductor looks like that. So we have to be real careful when you draw the resistor that you're nice and crisp, so it doesn't end up looking like an inductor. Okay, the capacitor and the inductor, these will store energy. Okay, the capacitor stores energy in an electric field. The inductor stores energy in a magnetic field. So it's a little more complicated. We're going to wait till later in the term before we tackle those. A lot of things, like a motor, is going to be made up of a couple of these. It's going to probably be resistive in nature and inductive in nature. So it's not uncommon for things to take on all of these things. There are some things that are predominantly resistive. There are some things that are predominantly inductive. And probably a resistance heater is a good example of something that's fairly resistive. A motor is something that's really predominantly inductive in many cases. Well, so we will get to capacitance and capacitors and inductors, but I'd like to first start our work with resistors. So with resistors, so I'll rewrite this. We already saw the symbol looks something like that. You want to draw it nice and crisp, but don't confuse it with an inductor. We'll give it the value R, and we're going to say that the resistance R is given by rho, the resistivity, times the length divided by the cross-sectional area. So if I have some sort of a conductor, some sort of a wire, it has some cross-sectional area. It also has some length, and rho, the resistivity, that's a property of the material. We would think that glass has a much greater resistivity. It's a better resistor than it is a conductor, whereas copper has a low resistivity. It's a better conductor than it is an insulator. Okay, so there's how we calculate the resistance. This is going to have units. Messed that up. It's going to have units of ohms, named after George Ohm, and we give the symbol like that. Okay, and a lot of times we have these devices. They can take on a variety of different shapes, but a lot of times they'll have some color codes on it, like that. And it's a purpose-built resistor, and we'll talk about those color codes in lab. You'll get a chance to use a lot of those. It would have some resistance. And sometimes if you just have some wire, you have losses due to resistance. If we're going to run electricity from here to Staten or somewhere else, something like that, going to have a lot of wire, going to have some resistance. So sometimes we very purposely put resistance into things. Sometimes resistance creeps in as losses, and you could calculate that using that equation there. Let's see. We should probably, I guess we've got ohms, so we probably want Ohm's law, right? With Ohm's law, we have that the voltage V is equal to the current I times the resistance R. So if I take this resistor, whether that's a purposely placed resistor or whether that's some inadvertent losses, and it has some value R in ohms, and I have some current I going through this, so I've just taken a section of a circuit here, I've got some current I going through there, it's going to produce a voltage drop across here. It's going to go from positive to negative, because remember that I is positive charge. It's going to flow to the negative side. So that's Ohm's law. If you have a resistor of, let's say, 10 ohms, and resistor values, they can go from fractions of an ohm. If you just have a short piece of wire, it's probably going to be a tiny fraction of an ohm, to hundreds and millions of ohms. So we could talk about k ohms. We could talk about mega ohms. Well, let's say, keep the math easy here. Let's say that I have 10 ohms and I have 3 amps traveling through that. That's going to give me what? 30 volts. A drop of 30 volts across that. That's how Ohm's law works. Well, eventually we're going to combine Ohm's law and Watt's law, but before I do that, I guess I should probably talk a little more about this resistivity. What's actually the, if we look at the resistivity of something, so reproduce this here. If I get the resistivity, okay, that's close enough. So our resistivity there is how good a measure of how good a conductor it is. Okay, what's the best one? It's always better when it's to have a lecture in class and you start to get students chiming in and whatnot. Usually, students will say, "Well, gold." What's that? AU on the periodic table, I think. Gold is pretty good. It's not the best. Gold is pretty good. Oftentimes you'll see gold connections. I think that's why students sometimes think that gold is good because they use it on connections in integrated circuits or high-end stereo connections or something like that. Gold has the advantage it's fairly corrosion resistant. It's also very malleable. So in terms of integrated circuits, you can shape it to very, very small dimensions. It's the most malleable material. The actually better than gold is copper. What's that? Cu? That's actually better than gold, so which is kind of nice. So you go down and buy an extension cord, it's probably copper. That's a very common one, relatively inexpensive, certainly way less expensive than gold. Actually, the number one is silver. And what would that? That'd be Ag, I think. That would be Ag. Yeah. If we go down the line here, we've got. Let's see, is aluminum better than platinum? No, yeah, so aluminum is a little better. We've got iron, aluminum, platinum. Okay. Sometimes students will say, well, platinum is the best. Well, platinum is the least corrosive. So if you're worried about contacts corroding or something, platinum is going to be your ticket. But it's not that great a conductor. Not nearly as good as copper. Certainly not as good as silver, although silver corrodes readily. Aluminum, it's not nearly as good as copper. Certainly lighter. They tried some wiring, having the branch circuits in houses in the 70s, 1970s. Using aluminum wiring, and the problem with aluminum is it creeps. So you take a piece of wire and strip down the insulation here, and you then tighten this screw onto this. Okay. If you have a copper wire, or for that matter an iron wire, that's fairly uncommon, but you tighten it down, you come back in 10 years, still just as tight as it can be. But if you put aluminum in there and tighten it down, it actually creeps, it flows like silly putty might, and it gets loose, and then you get some heat in there, you get some aluminum oxide, and it's kind of a vicious circle. You end up with a fire going in there. So aluminum can be problematic in that region. But silver is the best. Copper is a close second. So we look at this chart with this direction is good conductors. Which means that this direction is good insulator, right? And certainly way, way, way down. Iron would certainly not be considered a good insulator, but we'd have things like rubber and glass and so forth. Okay, which brings us to a concept of that's the opposite of resistance, that being conductance. Conductance is actually equal to 1 over the resistance, and we give that the symbol G. It has units of Siemens, or you can write that as the upside down ohm symbol. Okay, so something that has good conductance, that or high conductance, that would be like silver, would have low resistance, we see with this equation. Something like glass that has high resistance would have low conductance. Okay. Now, nothing is a perfect conductor. I guess we can talk about not talking about superconductivity, but just talking about things at room temperature and whatnot. Nothing is a perfect conductor, nor is anything a perfect insulator. We start looking at very high voltages, they'll try that pressure that we saw before will try and push through that insulator, and it will begin to break down. So we don't necessarily have perfect conductors, we don't necessarily have perfect insulators. But that's how resistance and conductance fits together. Well, like I mentioned, next time we get together, we're going to put together Ohm's law and Watt's law and see the implications of that, and start to put some of this together in some examples. So thank you for watching, and take care till then.